Jai Hind everyone. This is the second lecture of the subject Special Electrical Machine. If you remember, we have discussed the introduction and the vast application areas of special electrical machine in the very first lecture of the subject. So in this particular lecture, I am starting with the content of Unit 1. The Unit 1 content is we must have the concept of constant torque and constant power controls. This is in reference with the three-phase induction motor. Then three machines that we are going to cover in this particular unit are the induction generator, the linear induction motors, and the two-phase AC servo motors. So in induction generators, basically the special electrical generators, which is self-excited induction generator and the doubly fed induction generator. So let me start with the concept of constant torque and constant power control. So concept of constant torque and constant power controls. If you remember the V by F control of three-phase induction motor, you have gone through during your 5th semester in the subject of electrical machines too. So in an induction motor, constant torque control means maintaining a consistent output torque across a particular range of speed, typically at lower speeds. Lower speeds means below the base speed, right? Below the base speed, that is below rated speed of the motor. The base speed is obtained or rated speed is obtained when we are operating the motor at rated frequency. So below the rated frequency, below the point of rated frequency, the control obtained is constant torque control. We have to maintain during this period when we are operating the motor with variable voltage and variable frequency control. When we are operating a three-phase induction motor with variable voltage and variable frequency, then we maintain the ratio V by F constant below the base frequency or rated frequency, right? And above the rated frequency, only the frequency is increased while voltage is maintained constant at the rated value, as you cannot operate the machine continuously at a voltage which is more than the rated value. So beyond base frequency, beyond rated frequency, you cannot maintain the ratio V by F constant, right? So in V by F control of the motor, the reason below the base frequency was the constant torque control reason, and in this reason, a consistent output torque across the range of speed up to the rated speed was maintained, right? So this is done at the lower speeds, while constant power control refers to keeping the output power constant as the speed increases. As I just told you, in triple VF control, we increase the frequency given to the motor beyond the rated value while maintaining the voltage at the constant value. Constant torque reason, as I told you, below the base speed of the motor where V by F, just a minute. So below the base speed of the motor where V by F, voltage to frequency ratio, is kept constant, ensuring the magnetic flux remains relatively stable and thus producing a consistent torque regardless of the speed of the motor. And the various applications where constant torque operation is required are conveyors, crushers, pumps, all operating at the low speed. You might have remembered in context with this, you know that phi is proportional to V by F. So maintaining V by F constant will maintain flux phi substantially constant. Constant power reason. Above the base speed where V by F ratio is gradually reduced as we are maintaining V constant at the rated value while we are increasing the frequency, there would be a reduction in the ratio V by F and hence a reduction in the air gap flux of the machine. So machine is operating with reduced flux and hence the torque production capability of the machine is compromised. During this operation of the machine is actually operating at constant power which is delivered by the machine. Various applications are fans, centrifugal pumps operating at high speeds, where power demand remains relatively constant despite of the increasing speed. Selecting the appropriate control mode, whether it is constant torque control or constant power control, actually depends on the load characteristic, where if it requires consistent torque at varying speeds or constant torque at increasing speeds. So, whether we have to operate the motor in constant torque region or in constant power region, this entirely depends upon the requirement of the load, whether the load is requiring constant torque operation or the constant power operation. Now, moving ahead, let us start with the second topic of the unit, which is induction generator. So, we have to understand the operation of self-excited induction generator and doubly fed induction generator. So, before going into the details of self-excited induction generator and doubly fed induction generator, let us just recall the basic principle of operation of an induction generator, right? So, a three-phase induction motor, we know that well, that converts electrical energy into mechanical energy, but when the same machine starts converting mechanical energy into electrical energy, it is said to be an induction generator. How it happens? When the three-phase supply is given to the stator winding of a three-phase induction motor, a revolving magnetic field is reduced in the stator core as well as in the air gap of the machine, or I must say in the magnetic circuit of the machine. This magnetic field rotates at the synchronous speed, you know that well. Current is induced in rotor conductors and torque develops by the interaction of the stator and rotor magnetic fields, and the rotor starts rotating. Now, if the same rotor is decoupled from the load, or if the same motor is now coupled with an external prime mover, and this prime mover starts rotating the rotor at a speed which is more than synchronous speed ns of the machine will start acting as a generator. Remember, the machine is still connected to the existing grid, and this is the unique operation of an induction generator, that it draws the reactive power from the grid and at the same time it starts supplying the active power to the grid if the rotor is rotated at a speed which is more than the synchronous speed. If the rotor is rotated at a speed which is more than synchronous speed with the help of an external prime mover coupled with the shaft of the rotor, the machine will at this stage the machine is before accelerating to a speed which is more than synchronous speed, the external prime mover will start accelerating the rotor before attaining a speed which is more than the synchronous speed. The rotor attains the synchronous speed itself. So, when rotor is rotating at the synchronous speed, there is no exchange of power between the machine and the grid. At this time, the machine is said to be floating on the grid and floating on the bus bar, and machine is neither receiving nor supplying any power to the supply system or to the grid or to the bus bar or to the load connected to the bus bar. If the rotor is further accelerated, as I just told you, the rotor speed is increased beyond the synchronous speed, the slip S will become negative, which is given as ns minus nr upon ns, nr being more than ns, the slip will become negative. Right? The rotor conductors will generate current in opposite direction as they are cutting stator magnetic field due to the relative speed between rotor conductors which are rotating at a speed more than the synchronous speed and the stator produced magnetic field which is rotating at a speed equal to the synchronous speed. This generated rotor current produces a rotating magnetic field in the rotor which applies thrust on the stator field in opposite direction. So consequently, an EMF is generated in the stator winding, and this EMF is larger than the applied voltage and it acts in opposite direction. So it pushes the current to flow from the stator winding to the supply system or to the grid or to the bus bar to which the machine is connected. In order to develop rotating magnetic field, it requires magnetizing current and draws reactive power from the mains, as I just told you, right? So, at the same time, this is a special operation of the machine. When the machine, for its operation like an induction generator, the induction machine should remain connected to the existing supply system. Otherwise, there would not be any source and hence there would not be any reactive power for the development of flux in the magnetic circuit or in the air gap of the machine. So, the machine, at the same instant, machine is supplying active power to the mains as shown in the figure. The machine is acting as a generator. It is supplying active power to the supply system or to the grid, and at the same time, it is absorbing or it is drawing reactive power for the development of air gap flux in the machine. So, this particular operation shows that induction generator cannot work, cannot operate in isolation because it continuously requires reactive power from the supply mains. But this problem can be solved by connecting a capacitor bank to supply reactive power equivalent to the reactive power which was earlier supplied by the supply mains to the motor. So, by connecting a capacitor bank across the stator terminals will serve the purpose of reactive power requirement for the establishment of air gap flux in the machine. So, let us now move to the isolated induction generators. The isolated induction generator is also called a self-excited induction generator or SEIG. It is called self-excited because in isolation, when the rotor of induction generator is rotated at an enough speed, a small voltage is generated across the stator terminals due to residual magnetism. The operation starts with voltage build-up in the generator because of the residual magnetism. The machine is now operated in isolated mode, and the isolated mode means it is not connected to the existing supply system or to the grid. The machine, when it is not connected to the grid, let it be induction generator or let it be synchronous generator, then it is said to be operating in the isolated mode. So, for operation in isolated mode, what is there? We need to connect a bank of capacitor across the stator terminals as shown in the figure. But for voltage build-up in the induction generator, when we are starting the machine, a residual magnetism must be present in the magnetic circuit of the machine. So, because of presence of this residual magnetism, when the rotor of the machine is rotated, a voltage is induced in the stator winding due to the presence of residual magnetism. If the bank of delta connected capacitors is operated in parallel with the induction generator, then the reactive power requirement of induction generator is met by the capacitor. The arrangement is shown in the figure, but the initial voltage buildup is only due to the residual magnetism present in the magnetic circuit of the machine. So, in case of self-excited generators, the bank of delta connected capacitors supply the necessary magnetizing current for exciting the generator. With the load put on the generator, the operating frequency of the stator changes and it depends upon the rotor speed and is affected by the load as well. The voltage is primarily decided by the capacitor's capacitive reactance at that particular operating frequency. The equivalent circuit of the generator is also shown in the figure here. So, it is just like the equivalent circuit of a 3-phase induction motor. See resistance R1, the per phase value of the stator winding resistance, reactance X1, per phase value of the stator winding reactance. X2 dash is the per phase value of rotor reactance referred to stator side. R2 dash is per phase value of the rotor resistance referred to stator side. The magnetizing reactance is shifted at the input terminals to make it an approximate equivalent circuit. The resistance, the core loss resistance branch RC is not shown over here as it is not required. Now you see over here, this branch is representing the capacitance of the capacitor bank connected across the stator terminals, and RL is the load resistor. So this is the simple equivalent circuit representation of self-excited induction generator. Now let us try to understand how the voltage build-up takes place in an isolated induction generator. So we know that induction machine can also work as generator without any external supply. This is called the isolated operation of the induction generator. And as I have told you, to provide the necessary excitation in the machine, a delta connected capacitor bank is connected across the terminals of the stator. This was shown in the figure as well. Now, the presence of residual magnetism, as I told you earlier, the presence of residual magnetic flux is necessary to provide the initial excitation in the machine. So, if there is no residual magnetic flux, then initially we have to operate the machine as an induction motor so that some magnetic flux is retained while converting the operation of induction machine from induction motor mode to the self-excited generator mode. To start the machine action as a generator at no load, the machine is made to run slightly above the synchronous speed with the help of some prime mover. Prime mover can be anything. It can be a turbine, a hydraulic turbine, a wind turbine, or any other turbine, or it can be a diesel generator or IC engine based generator, or anything which is capable of providing mechanical rotation to the machine. Consequently, a small EMF is induced because of presence of residual magnetism in the magnetic circuit. So, a small EMF is induced in the stator, and the frequency of this induced EMF would be proportional to the speed, operating speed of the rotor. The induced voltage in the stator appears across the delta connected three-phase capacitor bank, and this gives rise to establishment of a leading current drawn by the capacitor bank, right? This leading current is equivalent to the lagging current supplied back to the generator. So, the flow of current between stator winding and the capacitor bank is actually the magnetizing current, is actually serving as the magnetizing current for the generator. So, a magnetic flux is set up by this current, which assists the initial residual magnetism, causing an increment in the net flux of the machine and hence an increment in the induced EMF of the machine. So, this increase in induced voltage causes further increment in the terminal voltage. The terminal voltage is also appearing across the capacitor bank. So, this causes an increment in the current, an increment in the capacitor voltage as well. The current drawn by the capacitor increases. So, this voltage build-up by induction generator continues to a point where the magnetization of characteristic of the machine and voltage current characteristic of capacitor bank intersect each other. The characteristic is shown on the next page, next slide. So, this is the characteristic. Here you can see this is magnetization curve of the induction generator. This is the VI curve of the capacitor, VIC curve of capacitor, right? So, the intersection point of the magnetization characteristic and VI curve of the capacitor bank gives this as the operating point of the machine, and corresponding to this, V1 is the induced voltage and IC1 is the capacitor current. This capacitor current is serving as the magnetizing current for the generator. So, this is basically the magnetizing current flowing in the stator winding of the machine, and this is the induced voltage. And this is the as per this particular operating point over the curve. At the point of intersection of magnetization characteristic of the machine and VI characteristic of the capacitor bank, the reactive power demanded by the generator is equal to the reactive power supplied by the capacitor bank. So, it gives you a stable operating point of the machine. The operating frequency of induction generator depends upon rotor speed and is also affected by the load. The voltage regulation of an induction generator is mainly governed by the capacitive reactance of the capacitor bank at the operating frequency of the machine. Now, this induction generator, the self-excited or isolated induction generator, suffers from a very serious disadvantage, that is, for a load of lagging power factor, the voltage of induction generator collapses very rapidly because of the large voltage drop. Now, here are certain key points related with the isolated or self-excited induction generator. What are the various key points? Let us focus on the advantages of the generator. So, the various advantages are: they do not require commutator and brush arrangement as it is needed for synchronous generators, and hence they are more rugged in construction. The induction machines are most rugged machines as compared to the other conventional machines like DC or synchronous. They are simple and robust in construction and operation, both mechanically and electrically, and then other generators. They are robust in construction as well as on operation as compared to the other counterpart generators like DC or synchronous. The low cost and maintenance, they have low cost and the maintenance as compared to the synchronous generator, and effective for small and medium power applications ranging typically up to a few hundred kilowatt. There are certain disadvantages as well. So, these generators actually suffers poor voltage and frequency regulation. The output voltage and frequency depends upon load as well as rotor speed, and any change in load causes a variation in voltage as well as a variation in voltage and frequency. These generators rely on residual magnetism in the rotor for initial excitation. If the residual magnetism is lost, what can be the reason of losing the residual magnetism? It is due to the long storage or the demagnetization of the generator. So, the generator will fail to self-excite unless it is remagnetized externally so that it have some residual magnetism when we are starting the machine as a generator. Poor performance under variable loads, as I have mentioned as the first point as well. Load fluctuations actually results in fluctuation of the voltage as well as frequency. These generators do not allow independent control over voltage and frequency, because Both of them are actually dependent upon capacitor size, speed and the load conditions. So the voltage and frequency control is not independent or it is not decoupled in nature in case of self-excited induction generators. These generators need capacitor banks to supply reactive power for self-excitation. So, choosing a correct capacitor size is critical for proper operation and efficiency, and improper capacitor selection will lead to overvoltage or the undervoltage issues. Further, these generally have lower efficiency and power factor compared to the synchronous generator, and especially this happens under variable load conditions. These are the certain application areas for self-excited induction generator. So, they are commonly used in off-grid and standalone power generation applications where a reliable and cost-effective energy source is required. So, various applications are, they are used in small-scale wind turbines, particularly in the remote locations as they are rugged in construction, low in cost and require less maintenance as compared to the synchronous generators. So, a preferred choice for electrification of those remote locations is to have the induction generators, self-excited induction generators, because there is no grid supply to maintain the reactive power for other type of generator like doubly fed induction generator. Small hydro power plants, these generators are used in micro hydro and pico hydro power plants for rural electrification. Again, this is an application of the electrification of the remote area which do not have the access of the grid. These generators are ideal for providing electricity to remote villages, farms and isolated communities where grid power is unavailable. And it can also be used as backup power for agriculture equipment. They are also employed to run water pumps, threshers and grinders in off-grid locations in the agriculture system. So, that is all for this particular lecture, and in next lecture of the subject, I will discuss the operation of doubly fed induction generator followed by the two-phase induction motor, which is also termed as the two-phase servo motor or AC servo motor. Thank you.